Our next speaker is Dan Huber, and he's going to talk to us about the role of astrometry in improving the accuracy and the precision of exoplanet properties by improving the stellar parameters. If you only know your planet as well as you know your star. So, all right, take it away, Dan.
Thank you, Don. I took the liberty of shortening the title a little bit because it didn't fit on the slide. So there you go. I call it Astrometry and Exoplanet Host Star Properties. So it's a great pleasure to be back at the Sagan workshop. I actually remembered that 10 years ago, I was an attendee at the Sagan workshop as a participant, and I had a fantastic time. It was a very rewarding week as a young postdoc, and I hope all of you in the room will have a similar experience this week. So as Don mentioned, my job is to tell you a little bit about how astrometry informs fundamental properties of stars and why this is important for understanding the planets. There will be a lot more talks about this topic related to this topic tomorrow. So what I will try to do is to give sort of a pedagogical overview as to what are fundamental stellar properties, how can we actually measure them, and then at the end, I'll give you a few examples of how that propagates down to exoplanets. Okay, so let's start off with the question, what are stellar properties and how can we actually measure them? And in the spirit of a workshop and in having some audience engagement, similar to Todd, I'll pose a question to the audience in the room. I think this will mostly work for the people in the room, but perhaps online folks can also chime in. What are some examples of fundamental stellar properties that we might want to determine, in particular with relevance to exoplanets? So just feel free to shout out a few if you have any ideas. Mass, fantastic. What else? Temperature, age. What else? Metallicity, radius, fantastic. Yes, I think we've hit all the important ones. So these are the fundamental properties that we might want to know. We want to know the temperature. We want to know how big the star is. We want to know its mass. We want to know its metallicity, chemical composition, and other parameters that are related to it, surface gravity, luminosity, density, and very importantly, of course, age. Now, on the right-hand side are things that we can observe. We can observe the color, we can observe spectral type, luminosity class, rotation period, and things about the stellar multiplicity, which you've already heard about. But for this talk, we will really only focus on the fundamental properties, so the ones that are listed here on the left. So this list, of course, includes some fundamental properties that are correlated with each other. And many of these fundamental properties are actually not independent. So mass and radius is, of course, defines the density of the star. It also defines the surface gravity of the star. And we also have a relation between the luminosity, the radius, and the temperature of the star through the Stefan-Boltzmann law. So these three relations make some assumptions. They assume, for example, the photospheres are quite thin compared to the radius of the star up to the photosphere. And they assume that stars roughly radiate as black bodies, which is, of course, not exactly true. But for the purposes of this talk and for the uncertainties we're worrying about, we'll make that assumption and assume that it holds true. Now, one other important quantity about the relations between these fundamental properties is that there are actually three quantities on the left-hand side that define all other fundamental stellar properties that we might determine. And those are the mass, composition, and age. If you know the mass and the composition of a star from a modeling perspective, all you need to worry about is the age. You propagate the age of the star forward, and you can predict all the other fundamental properties of the star using that information. So to illustrate this, I'm going to show a brief movie of a model. This is from Rich Townsend's website of a sun-like star, a solar mass star, as it evolves off the main sequence and becomes a red giant. The left-hand side plot shows the temperature stratification within the star. So that's temperature as a function of mass coordinate or radius coordinate, which is actually a little bit less important. But the thing that I want you to keep an eye on are the properties down here. So the mass of the star, the age, and other properties that we might want to know, such as radius, luminosity, and temperature. And so given a mass and some initial chemical composition, all we need to do is we need to change the age and we can predict all other quantities. Those three quantities uniquely define the luminosity, the radius, the temperature, and hence the surface gravity and the density. Of course, the problem is that masses and ages and also some chemical abundances, for example, helium, are very hard to measure. Masses are, of course, fundamentally measured by astrometry, and that already gives you a hint as to why astrometry is so critical for fundamental properties of stars. Now, I can subdivide this list of fundamental properties that we've just discussed into categories of things that are quote unquote easy to measure. I use quotes here because actually nothing is really easy to measure about stars, but those are the easier ones: temperature, radius, and luminosity, things that are possible and things that are fundamentally quite hard to do for any given star. And we will start off with talking about the easy properties, so the effective temperature, the radius, and the luminosity. Now, these quantities, of course, are fundamentally connected to astrometry through the distance of the star. So one of the things that you can immediately calculate once you know the distance of a star and you have some kind of flux measurement of the star through photometry and some kind of bandpass is the stellar luminosity. This is done through the well-known distance modulus, which basically just requires you to know the magnitude of the flux in some bandpass, let's call it B. You know the distance to the star, so this is something that we can get, of course, from astrometry, and that allows you the only difference between the absolute magnitude of the star, so the intrinsic magnitude of the star at some set distance, to the apparent magnitude is only dependent on the distance. Of course, there is a complication in here, which is the effect of interstellar extinction that will change your apparent magnitude that you need to take into account. But assuming that you can control for this, one strategy that you might take is that you measure your apparent magnitude, you solve for the absolute magnitude. You then need to convert this absolute magnitude in the bandpass that you've measured it into a bolometric absolute magnitude. You can do this by applying a bolometric correction so that it accounts for the flux that you haven't measured in your bandpass. And then finally, you have some reference value for the bolometric luminosity of the sun, which allows you to calculate the luminosity of the star. So this method is very powerful. It's powerful because we have observables, the apparent magnitudes and distances, thanks to Gaia, for many, many stars. So you can simply solve this equation for many stars at the same time. The disadvantage is that you need to be confident in your bolometric corrections and in your extinctions. If you don't know this well, then these can propagate into systematic errors in your luminosities. Of course, you can also directly measure the bolometric flux. So instead of doing bolometric corrections, you can just try to approximate the spectral energy distribution of your star. You do this by measuring the flux in different bandpasses across the spectral energy distribution. You fill in the gaps with model atmospheres, and then you simply integrate underneath the curve to calculate the bolometric flux of the star as observed on Earth. And that allows you, together with the distance, to calculate the luminosity. This has the advantage of being less model dependent than bolometric corrections, but it also has a disadvantage. Most of the time you combine photometric passbands from different surveys. Those might have different 0-point offsets, and those propagate into systematic errors. Both methods have a challenge that includes the bolometric corrections, which is that both of them depend on the effective temperature of the star and extinction, which I've already mentioned, and so that degeneracies between those parameters. So if you want to solve for the bolometric flux, you can essentially get a similar answer if you make some slight changes to the temperature and the extinction. So this has been done in the past, of course. We've had photometric servers that allowed us to do spectral energy distributions, but it's really been and will be revolutionized by Gaia, not by the astrometry, but by the BPRP spectrophotometry that covers a large range of wavelengths where stars emit a lot of light, and Orla will talk a lot more about this tomorrow. So we have a way to get luminosities. What about sizes? Sizes are important. We've already heard about the transit methods. That, of course, depends on knowing the size of your star. The most direct way that you can measure the size, the radius of a star, is that you know its distance. So this is, again, where this geometry comes in. You know the distance of the star. And then if you also know the angular size of the star, so the apparent size of the star on the sky, you can straightforwardly solve for the radius of the star. So this is a direct linear measurement of the angular size and the physical size of the star. The challenge, of course, is that diameters of stars are very small. And so you need very high angular resolution measurements to actually measure these tiny sizes that stars, even the closest stars to us, have on the sky. The only way that this can be done in a large sense is through long baseline interferometry. And we will have a talk by Roxanne tomorrow. We'll go a lot more into detail on how this actually works. So in general, this is a very powerful method. It gives you direct radius measurement, but it's only applicable to a relatively small number of stars that are large enough to do this. And so the alternative is that you use the Stefan-Boltzmann law. I've already hinted at this before. If you rewrite it as a function of radius, you can calculate the radius as a function of bolometric flux and distance, simply the luminosity, and the temperature, the effective temperature of the star. So that then begs the question, what is this term? What is the effective temperature? And you can see it goes into the fourth power. So it's clearly important that you know your temperature well in order to get the radius using this method. Now, the effective temperature is one of those astronomy quantities that's a little bit funny to think about, but it's essentially a definition. Of course, stars have different temperatures. You've seen this in the movie I showed at the beginning, depending on where you look inside of the star. And so the effective temperature is a definition, and it's essentially a definition that characterizes the total radiative flux that's transported through the atmosphere. So mathematically, you write this as the integral of H, which is essentially you can think about as the radiative flux over all frequencies, over the entire spectral energy distribution. So this is, of course, the definition of the Stefan-Boltzmann law. So another way to think about this is that the effective temperature corresponds to a black body that's radiating the same amount as the total energy that the star that you're considering would have a temperature that's equal to the effective temperature. So how can we actually measure the effective temperature? Well, if you think about what the effective temperature, how it is defined, if it's the total radiative flux, we know that the flux itself, the total flux that's emitted by the star, is related to the bolometric flux that we observe here on Earth by the ratio of the distance from the star to the radius of the star squared. Now, the radius of the star we've just defined, we know is related to the distance of the star and the angular size, which we call alpha, or called alpha in the previous slide. And so we can substitute in radius into this equation for the total radiative flux and rearrange the equation to give us the effective temperature as a function of observables, things that we can actually measure. And it turns out that distance is actually not involved in this. So here is actually a case where geometry, and knowing that distance is not directly related to a fundamental property, temperature is defined for the bolometric flux and the angular size of the star. So the only way that you can measure, as defined, the effective temperature of the star is if you measure its bolometric flux and you know its angular diameter. Of course, we'll hear about for how many stars we can do this using interferometry. But of course, this is not possible for most stars. And so for most stars, we need to use other methods to get at the effective temperature. And so two very popular methods to do this is that, for example, you take a high resolution spectrum of your star, which is shown up here. You measure the depth of the absorption lines, and the relative depth of these absorption lines tell you something about the temperature and, in a sense, the effective temperature of the star. You can also construct so-called color temperature relations. So those are relations that relate the effective temperature of the star to a color. So this is simply using the shape of the spectral energy distribution as the shape of the black body curve changes with temperature, relating that to a color. And there's various different ways to do this. Color temperature relations, SCD fits, something called the infrared flux method that some of you might have heard about and I won't have time to go into. But all of them are essentially you can define as photometric methods of measuring the effective temperature. And one important thing to take away is that the effective temperature from these different methods can vary significantly. So here's a plot that shows the differences in effective temperature measured using different methods as a function of some reference effective temperature. And you can see that if you subtract different methods to do this measurement, photometric and spectroscopic, you can get differences on the order of a few hundred Kelvin, which at solar temperature corresponds to about 2% roughly in temperature. And if you remember the Stefan-Boltzmann law, it goes into the fourth power. And so that means that this sets, or it goes into the second power. So this sets a floor in the precision that we can reach, and in fact, also the accuracy, if you think about the absolute scale, of about 4% on stellar radii. So even though we have these really precise distances, it's important that there are other factors that limit the precision of what we can get for stellar radii. Of course, 4% is still amazing, right? We should not discard the fact that we can now measure radii of stars to 4 or 5% for hundreds of thousands of stars in the sky. And that has really made a huge impact on stellar astrophysics. We'll hear more about this tomorrow, but also exoplanet science. So to show you one example, this is an HR diagram here on the left. It's not quite an HR diagram. It shows the surface gravity, but you can think about it as an HR diagram of the Kepler stars. So those are the 200,000 stars that Kepler has observed. On the left-hand side is pre-Gaia, and on the right-hand side is after we have incorporated Gaia parallaxes. And you can see that the colors are basically the density of the stars. Pre-Gaia, we really didn't have any clue about the luminosities or the radii of most Kepler stars. And probabilistically, we thought, okay, well, maybe most of them are fairly close to the main sequence, which is where you see this red distribution here. But with Gaia, we now actually have this beautiful HR diagram where we can exactly pinpoint where the stars are, how much they have evolved off the main sequence. And we can also, of course, see many other structures from stellar evolution, such as the red clump, much more clearly. One other thing that jumps out of this plot, which is actually a challenge, is that with Gaia, with these very precise distances, we now are in a position where we actually have to worry about binaries and multiplicity. Pre-Gaia, when we did Kepler stellar characterization, we didn't even worry about the binaries because just single star radii were hard enough. But now with Gaia, we have to worry about binaries. And so unresolved binaries will bias your luminosities and also your temperatures. And so the general effect is that the luminosities will be over-predicted if you have an unresolved binary in your photometry. And you can see this very clearly in this secondary sort of main sequence hovering above the M dwarfs. Todd also showed an example of this earlier today. So this is something that you need to take into account. It's a challenge, but it's also an opportunity. Of course, it allows us to study properties of planets and properties of stars as a function of stellar multiplicity. Okay, so moving on now to fundamental properties of stars that are hard. So I've talked about the easy ones so far. What about the ones that are harder? Mass, gravity, density, and age. Masses are, of course, fundamentally related to astrometry, and astrometry allows us to fundamentally measure masses of stars. I'm showing here an example from HST. This is actually a visual binary where we can use observations such as the ones with HST to map out the orbit on the sky. So this is MuCAS, a very famous metal poor solar type star, a K-dwarf in the solar neighborhood. And you can see this beautiful astrometric orbit that has been mapped out here over decades using HST. And just to give you an idea, I've copied the table of the masses that have been determined down here. It's a little bit small to see, but basically the masses from both components using this astrometric data have been measured to 1 to 2%, which is really remarkable. Of course, Gaia will contribute to this, and there's an aptly paper in Gaia DF3 called A Hidden Treasure, which shows 100,000 astrometric solutions of binaries. Of course, there are many other binaries that Gaia is actually sensitive to, including spectroscopic binaries, eclipsing binaries. This is a plot showing the eccentricity versus orbital period for all the binaries that are part of Gaia DR3. The astrometric ones are shown here in purple. So this will be a treasure trove of data sets to determine masses of stars. Of course, you need, in many cases, supplementary information to actually get at the individual masses, but it will be a huge leap forward for actually fundamentally measuring masses of stars. What if you don't have a binary star? Well, there are some other alternatives that you can do. I want to briefly mention astroseismology. Many of you know this is near and dear to my heart. If you don't have a binary star, you can use pulsations, stellar pulsations of stars to get at densities, log Gs, masses, and ages. The way that this works is that essentially stars pulsate, they oscillate, the observable quantity of brightness variations. So this is a power spectrum, a Fourier transform of a Kepler light curve, and each of these peaks is a pressure wave that propagates through the interior of the star. And these pressure waves are sensitive to the sound speed within the star, the sound speed profile, and the sound speed profile itself depends on fundamental properties of the star. Without getting into too much detail, astroseismology can measure the density of the star. It can also give you an idea of the surface gravity with some dependence on temperature. But most importantly, perhaps, this so-called small frequency separation, which is one of these separations of the peaks that you see, is sensitive to the gradient of the sound speed, which is shown here as C, near the core of the star. And so as the star burns hydrogen to helium, that sound speed will change, and the small frequency separation will be sensitive to this. So Gaia itself is actually still very valuable for astroseismic analysis. And the reason for this is that oftentimes astroseismology actually allows you to test some of the model physics that go into constructing these 1D evolution models. And having an independent constraint on the luminosity is actually very important for this. So one of the things that we, for example, would like to measure is the convective mixing length parameter that parameterizes how efficient convection is. This is one study that has been done pre-Gaia, trying to measure this convective mixing length parameter as a function of temperature. And it is difficult because there are degeneracies with other fundamental stellar properties that prevent you from precisely measuring these quantities. And so including an external constraint on luminosity or radius from Gaia is very valuable to do this. And I expect that this will happen more and more in future studies using astroseismic data sets from Kepler and other missions. Okay, so, but what if you don't have a binary star and you don't have Gaia, and you don't have astroseismology? What do? Well, you go to stellar models and you essentially perform what's commonly referred to as isochrone fitting. This is a little bit of a misnomer actually, because models are generated generally, as I've shown before, at a fixed mass. So evolutionary tracks are actually the fundamental quantity that we calculate. Isochrones, as the name implies, are actually models at fixed age and varying the mass. But the fundamental, that aside, the fundamental idea is the same. You generate a model that has some mass, age, and composition that predicts quantities and that you can compare to your observations. So that includes temperature, metallicity, and luminosity, for example. And so you basically take your models and you put your observations down, and you use some inference methods to get posterior distributions, for example, of the age of the star, as shown here at the bottom. So this is a fairly well-known and well-adapted technique. There are many software tools out there. If you're interested in this, I've listed a few of them here. This is an incomplete list. If you're interested in knowing more about it, please come talk to me afterwards. One of the things that I'm not mentioning here are other age diagnostics, and that includes rotation, chemical abundances, kinematics, and clusters. Those will be talked about by Melissa and Marina tomorrow. But one thing I want to say about stellar evolutionary models in general, and as a note of caution, is that these models have systematic errors, and we should be aware of these. So if you take your Gaia-derived luminosity and your temperature and your metallicity, and you fit your star to your stellar model, and you get an answer for your mass and age, you need to be aware that these models that you've used might not give you the same answer as some other sets of stellar models. And the reason for this is that the input physics are unknown or uncertain in many cases. So here's an example. This is a recent paper by Jamie Taylor that showed the differences in mass across the HR diagram, luminosity, temperature, for different kinds of models. So this is a set of 4 or 5 different evolutionary models, and calculating what the mass differences are in percent at different parts of the HR diagram. And the main takeaway is that these differences are on average, it depends on where you are, but on average about 5% in mass, and that translates into a floor of about 20% in age. So if you know if you get your masses and ages to better than 5 at 20%, you should be cautious of these effects. M-dwarfs are, of course, everyone's favorite stars, especially if you care about exoplanets. M-dwarfs are also a major challenge for stellar astrophysics. So everything I said about models before, if you work on M-dwarfs, you might want to think twice about using stellar evolutionary models. They're getting better, but the common adoption for M-dwarfs is to use empirical relations, so relations that connect things that you can easily measure, the absolute magnitude, for example, to the radius of the star, and also to the mass. So you can construct temperature, luminosity, radius, mass relations. You can do this because M-dwarfs barely evolve or don't evolve at all over very long timescales. This would not really be possible for sort of more evolved sun-like stars. So these are calibrated with angular diameters, bolometric fluxes, dynamical masses, and very powerful. So this is the go-to method if you have an M-dwarf and want to characterize it. But one thing to keep in mind is, of course, that these relations are only as good as the sets that have been used to calibrate them. Okay, so wrapping up with the stellar properties discussion, here's I call it a cookbook for deriving stellar properties. And so this is one way to think about this. This is the way I think about it. Maybe others may have other preferences of how to go from your observables to your stellar parameters. I'll briefly walk you through it. So basically, for most stars, you will have a high resolution spectrum. You will have some spectral energy distribution, photometry, and you will have a parallax. And so that gives you a temperature, log G, a metallicity. The photometry gives you a temperature, an extinction, and a bolometric flux. And the parallax, of course, gives you a distance. The first thing to do is to ask, are your temperature values consistent with each other? Is your photometric temperature consistent with your spectroscopic temperature? If the answer is yes, you're good to go. You can combine your bolometric flux with your distance to get a luminosity. You can combine that with your temperature to get a radius. If the answer is no, you might think about, is extinction an issue? Are you observing a star that's in a highly extincted field? And depending on whether the answer to that question is, you might want to redo your spectroscopic analysis with a photometric temperature prior or vice versa. Assuming that you're good with your temperature, you can then, of course, feed this into a stellar evolution model. You get density, log G, mass, and age. You might ask yourself at that point whether the log G that you derive is consistent with the log G that you got from your high resolution spectrum. Right? If your high resolution spectrum has a giant-like surface gravity, you might want to reevaluate it if your evolutionary model in Gaia tells you that the star is actually a dwarf. But assuming that you're good, you can then do the last step, which is what I mentioned before, which is to use different evolutionary models to get a handle on systematic errors. And once you've done that, you're basically done and you're good to go with your stellar parameters. Okay, so in the last 10 minutes or so, with this sort of recipe in hand, I now want to talk a little bit about stellar properties and their impacts on exoplanets. And this is, of course, a huge topic by itself. But going back to this list that I started with, this list of fundamental properties of stars, we can ask which stellar parameters are most important for understanding exoplanets. So this is again a question for the audience. What do you think? Which ones of those are the most important ones if you want to understand your exoplanet? Oh, there's a strong mention of radius, but I heard something else. Mass, yeah. Okay, we see radius and mass, I think, are the winners here. I would argue that all of them are actually important. So the right answer was to say all of them. And this is true if you think about it. In any case, and I'll show you a few examples, in any case, all of these fundamental properties are important for understanding exoplanets. And the main reason of this is, of course, Don mentioned this at the beginning, is this mantra, know thy star, know thy planet. And this is because most of the detection techniques that we currently have detect exoplanets in a relative way. So I've shown some of these up here. Of course, transits, radial velocities, microlensing are all indirect. I don't have a plot for astrometry up there. Of course, we will we will see many more detections coming out of this. Of course, astrometry is also dependent. You need the mass of the star in order to get you solutions for the mass of the planet. And direct imaging is also included here. Direct imaging by the name, of course, means that we're actually directly detecting the planet. But as I'll show at the very end, stellar properties are still important even for this method. So in addition to just the sort of simple connection where you say determining the properties of the planet relative to the star, there's also a huge amount of information that we can learn from correlating properties of stars to planets about planet formation. A lot of demographics that can teach us about how planets form are connected to fundamental properties of stars. I won't talk about this here, but Jesse will talk about this a lot more tomorrow. So going into one specific example where stellar properties help you with transits is the fact that transits, of course, measure the sizes of stars or sizes of planets relative to the star. But there are other observables. So we have the transit depth, of course, and we have transit durations that we can measure. So we can measure the duration of the ingress and the flat part of the transit and the egress. In addition, we can also measure what's called the impact parameter. So this is where the transit happens with respect to the equator of the star. And so many of you will have seen this equation, which is that the depth of the transit is equal to the radius ratio of the planet to the star squared. But this equation actually only holds in a sort of idealized picture. And this is the picture that you see up here, which is that the star has a completely uniform intensity across the stellar disk. Of course, this is not what stars actually do. Real stars look like this. This is our sun. And you can see that the intensity distribution across the star is not even. And we observe an effect called limb darkening, the fact that the star is darker at the limbs than in the center. There's also spots, of course, on the surface of the sun. Those cause a huge amount of other problems that are mostly affecting measurements of planet radii as a function of wavelengths. So if you're interested in atmospheres, planetary atmospheres, I won't be talking about these effects here. The one effect that I want to mention is the fact that if you measure a planet, and if you imagine a planet that has an impact parameter of 0, you might measure some transit depth, and you can call that delta 1. But if you then have another planet with the same radius, so a fixed RP over R star, that transits at a lower impact parameter, then the transit depth that you will measure will be different because the planet is transiting the star at a fainter part, closer to the limb, than it is in the center. So that basically means that the simple relation between depth and RP over R star, which is what we need to get to the radius of the planet, right, is not quite as simple as this equation that I've shown on the previous slide makes it believe. However, luckily, there's a way to actually derive the impact parameter. So the impact parameter is really critical. To get a good radius ratio, RP over R star, to get a good radius of the planet, you need to know the impact parameter. But luckily, stellar parameters can actually help us to do this. So without a rigorous derivation, I've given the reference to the seminal paper up here for those of you who want to work through it. But if you assume circular orbits and the fact that the radius of the planet is much smaller than the star, and that's much smaller than the orbit, you can show that there's a relation between the transit duration that you measure, t, the transit duration for a central transit, so when b equals 0, and the impact parameter. And in addition, you can show that the b equals 0 transit duration is related to a quantity that is R star over A, so the ratio of the stellar size to the semi-major axis. The period, in most cases, we know really well, of course, from transits. Now, you can rewrite A over R star using Kepler's third law. It's basically just take A over R star, substitute in Kepler's third law, and you can show that there's a relation between A over R star and the mean stellar density. So you can write that A over R star, which is one of the things that you can measure from the transit, is directly related to a fundamental property of the star, namely the mean density. So that has two important implications. The first big result here is that independent stellar parameters can be used to improve your transit parameters. If you know the mean stellar density really well, that means that you have a good handle on A over R star. That means that you know you have a good handle on what the transit duration for B equals 0 is. And that allows you, if you remember the previous relation, to constrain the impact parameter and hence get a better estimate of RP of R star. You can turn this around, of course, to also say, well, if I can measure the transits really well, if I can measure the ingress and the egress really well and independently constrain the impact parameter, I can actually use transit observables to constrain stellar parameters. I can measure the mean stellar density of a star, assuming a circular orbit. Now, this technique, assuming a circular orbit, what I just said, has actually been used to study the eccentricity distribution of small planets. So if you make this measurement, the transit-derived mean stellar density, and you compare it to the true mean stellar density of the star, the only difference between those two is the eccentricity. And so if you do this, you can show that the eccentricity distributions of single transiting planets and multi-transiting planets, which are shown here on the right, are actually different, and that informs our understanding of how these planets might have formed. The point I want to make here is that Gaia parallaxes should now allow us to do this for a much larger sample. This is a sample of stars where we have astroseismic mean stellar densities that are very precise. But with Gaia, we now have mean stellar densities that are pretty good, right? So mean stellar density goes in R cubed. If we say 5%, we can get the radius to 5% with 15% mean stellar densities for essentially every star that has a transiting planet. So we should be able to repeat this in a very powerful way for many transiting exoplanet systems. Okay, the last thing I want to mention is direct imaging. Direct imaging, of course, is direct, so it doesn't have the same dependence on radius and mass of the star, but it does depend on the age of the star. So here is an example of a directly imaged, the iconic HR 8799 system, where we see planets orbiting the star. And one of the things that is really important for interpreting the planets is to know the age, because these planets change, their temperatures and their luminosities change as they age. So they start off being very luminous, and then they become less luminous and cooler as they age. And so determining the masses of them requires you to know the age of the star. And then alternatively, if you know the mass of the planet, for example, through dynamics, you can actually start to probe different models. For example, these hot stars and cold star models that are indicated here on the plot. So age is really critical for direct imaging. You want to know how old your planet is in order to convert your direct measurement of the luminosity or also the spectrum into something that you can interpret and contrast to planet formation models. Now, the last point I want to make is actually sort of a bigger picture point in direct imaging going forward into the future, given that we are at a Sagan workshop, right? And Jas mentioned this at the beginning. In the far future, we will be imaging Earth-like planets around nearby stars. We will start to do this, hopefully, with Roman, the Roman coronagraph instrument, and eventually with the 6-meter class flagship mission that was recommended by the Astra 2020 decadal that will hopefully give us images like these, which are simulated solar systems around nearby stars at around 10 parsec or so. And one of the things that will be really critical for interpreting the atmospheric signatures that we might detect on these planets are actually ages. If we think about biosignatures, and one of the ways that we can conclusively tell whether biosignatures are due to life or whether some atmospheric features are due to life or not, actually relates to the age of the planet itself. So this is some work that I've done with collaborators, Josh Christiansen Totten and collaborators, where we've actually shown or we've tested one way to do this, where we measured, if you measure the atmospheric abundance of oxygen, for example, on planets around nearby stars, you can show that if those planets, say you have 20 planets where we've measured atmospheric compositions, if all of these planets are inhabited, you would expect a different correlation between the oxygen abundance as a function of age of the system than if they're non-inhabited. If they're inhabited, we expect the oxygen abundance to increase as a function of age, basically as a consequence of photosynthesis. And if they're uninhabited, then you would expect a different trend. You would expect the oxygen abundances to decrease as a function of age. So ages in a future where we have population level atmospheric spectra of Earth-like planets will be critical for interpreting biosignatures. Of course, the age error bars here are 10 to 20%. This is very difficult to do on a large scale, but hopefully in the future we'll be able to actually achieve this. Okay, so I'm at the end. So at the summary, I've hopefully convinced you that astrometry from Gaia has revolutionized our way of determining fundamental properties of stars. Luminosities and radii to something like 5% are now routinely possible, and the error floor is now set by bolometric fluxes and effective temperatures. Masses and ages remain challenging. I think Gaia binaries will give us will be a huge step forward, at least towards testing the models that we use for single stars. And stellar properties are important for virtually all fields of exoplanet science. I've given you two examples. One is simple transit fits, how to get a better transit fit, and the other one is to actually a sort of big picture idea, which is interpretation of biosignatures in future directly imaged planets. And to wrap up, I just want to say, and I do this in every audience, but we have a lot of Gaia members. I want to say a big thank you to the Gaia team for this amazing data set, this amazing astrometric, but also other data sets, of course. As someone who spent a lot of time of my career trying to figure out radii and luminosities of stars, Gaia has been amazing. So thank you for all the work that you've done, and that enabled also this workshop. Okay, I'll stop there. Thank you.
Okay, questions for Dan? Come down and use, well, yeah. You need a microphone.
Can you go back to the image of the simulated resolved planets? Just one more, I think. Yeah, so how can one interpret the colors here on the right panel?
That's a very good question. I think there's someone in the room who could probably answer this a lot better than me. I would say, so this is a simulation for a concept, well, a future direct imaging mission. LUVOIR, I think, was this particular simulation. I don't think you want to read too much into the colors. The main takeaway is basically that in the middle, right, there should be a star. And one of the real challenges of direct imaging is that the star is much, much, much brighter than the planets, 10 to the minus 10 roughly, for sort of an Earth Sun analog. And so the main challenge is to suppress that starlight. I don't think the colors at the edges have any particular meaning, but I think Aki is in the audience and was involved in this. Can correct me if I'm wrong. But for the planets themselves, well, those it depends on the wavelength where they actually have been observed. So this is detections in reflected light. So this is the colors themselves will likely reflect sort of the atmospheric composition of the planets and their temperatures. But again, okay, correct me if that was wrong. Yeah. So one of our speakers and lecturers was involved in generating that simulation, and you'll hear a lot more about this, I guess, on Thursday or Friday, I think.
Okay, I'm gonna take a couple online questions, but while I do that, if you are giving a pop today, next, right, as soon as we're done with the questions here, please come down and line up here. Actually, I'll give Ellen. Ellen can help you get in the right order. So we're gonna line up here. Okay, so let's see. You gave a systematic floor of about 5%, 20% for mass, age, uncertainties. But how does this apply to relative masses and ages? How well do different model grids generally agree on which of two arbitrary stars are older or more massive?
Yeah, that's an excellent question. I think relatively you can definitely do better. And this is true actually for all stellar parameters. So if you want to measure relative radii and temperatures, which has been done, for example, using the California Kepler survey, which characterized Kepler stars and planets, you can do better than this for sure. So I think it's a good question, actually. It's hard to test in terms of, in a relative sense, how the models predict masses and ages. But I don't have a number, but I would say if you're just interested in relative ages and relative masses, those limits that I've given, 5 to 20%, are probably optimistic, and you can probably do better than that.
Okay, we're gonna ask one more because you give really nice short answers. Let's see, what's the best reasoning for different stellar models not lower confidence in mass and age certainties in specific regions of HRD? I'm assuming that's.
Yeah, no, that makes sense.
Okay, well, very good in some other regions in your paper with Terre.
Yeah, that's a very good question. So the question was basically why are the colors different across this HR diagram, right? Why do we do better in this part of the HR diagram and worse here? And the answer is basically the input physics that go into this. So some stars, for example, have convective cores if they're relatively massive. And so convective cores cause differences in the energy transport in the interior of the star. And so the convective core overshooting, which is one of the parameters that we use, is parameterized differently. M dwarfs, right? So stars that barely involve are generally hard to model. So the uncertainties in convection really come in here. So the reason that the colors get darker and darker here is essentially due to the uncertainties in modeling low mass stars. But you see some interesting features, and it's a good point. For example, here, but of sort of more evolved subgiants, the models actually seem to agree quite well. But it's essentially a reflection of different input physics in the models that play different roles in different parts of the HR diagram. So red giants, for example, you see are up here are not doing very well. Those are very unlike the sun, and so our input physics are least tested.
Okay, let's everybody think down again.